Assalamu alaikum, brothers and sisters. Welcome to the journey of quest where we quench your thirst of knowledge. Have you ever contemplated what causes the earth to crack and fracture? Welcome to a fascinating world beneath our feet where fracturing plays a significant role in shaping the earth's crust. This process, known as fracturing, is a focus of study in structural geology, a branch of earth science that examines the architecture of the earth's crust. At the heart of fracturing is the basic geometry of fractures. Picture this. A fracture is a planar crack in a rock, where the rock has split apart without the two sides sliding past each other. It's like a pane of glass that has been struck. The glass remains somewhat intact, but there's a clear, often jagged line where the impact occurred. But what causes these fractures in the first place? The answer lies in the stress within the Earth's crust. Our planet is not a static ball of rock, but a dynamic system with forces constantly at play. These forces, or stresses, are the result of tectonic activity, the movement of the Earth's plates. When the stress in a rock exceeds its internal strength, that's when a fracture forms. There are two types of stresses that can lead to fracturing: tensile and shear. Tensile stress pulls the rock apart, creating what we call a joint. This is the most common type of fracture and can be seen in cliff faces and road cuttings. Shear stress, on the other hand, causes one part of the rock to slide past another, leading to a fault. These fractures don't just occur randomly. They're a response to the pressures deep within our planet, forming intricate patterns that tell the story of the Earth's geological history. These patterns can reveal information about past tectonic events, the flow of groundwater, the formation of mineral deposits, and even potential sites for oil and gas extraction. So now we understand that fractures are not random, but a response to the pressures deep within our planet. Now let's delve deeper into the science behind these fractures. The mechanics of fracturing are intriguingly complex, yet fundamentally simple. They're governed by the principles of stress and strain. Stress, in geological terms, is the force per unit area applied on a rock, while strain is the deformation resulting from this stress. Picture this. A rock experiencing stress is similar to a piece of paper being pulled from both ends. The paper, or the rock in our case, deforms or changes shape in response to this stress. If the stress surpasses a certain threshold, the rock will fracture. But not all stress is equal. There are three main types of stress: tensional, compressional, and shear. Each of these types plays a unique role in the fracturing process. Tensional stress pulls rocks apart. Imagine stretching a rubber band. The more you pull, the thinner it gets in the middle until it eventually snaps. This is tensional stress at work, and it's responsible for creating fractures known as normal faults. Next, we have compressional stress. This is the exact opposite of tensional stress. Instead of pulling apart, compressional stress pushes rocks together. Think of squishing a marshmallow between your fingers. The marshmallow will bulge outwards, and similarly, rocks under compressional stress will form folds or reverse faults. Finally, we have shear stress, which works sideways. It's like taking a deck of cards and sliding the top half to the side while keeping the bottom half in place. The cards or rocks shift relative to each other, creating strike-slip faults. Each of these stress types, tensional, compressional, and shear, contributes to the fracturing process in its own way, creating a diverse landscape of geological structures. The interplay between these stress types and the inherent properties of rocks forms the core of our understanding of the mechanics of fracturing. Indeed, the stresses within the Earth's crust play a crucial role in the formation of fractures. But what happens when there are already existing fractures or faults in the crust? This query brings us to the fascinating realm of pre-existing discontinuities in the world of structural geology and geotectonics. Pre-existing discontinuities are essentially fractures or faults that already exist in the Earth's crust. These are not fresh breaks. Instead, they are lines of weakness that have been around perhaps for millions of years. Imagine them as the old battle scars of our planet, etched into the crust by the ceaseless forces of geology. Now, when new stresses are introduced to a rock mass containing these discontinuities, something intriguing occurs. These pre-existing discontinuities can behave like a double-edged sword. They can either inhibit or promote further fracturing depending on the conditions. Let's delve a little deeper. If the new stress aligns with the orientation of the pre-existing discontinuity, it can potentially reactivate the fault, leading to further fracturing. This is because the existing discontinuities serve as zones of weakness which readily give way under stress. On the flip side, if the new stress is perpendicular to the orientation of the discontinuity, it can actually inhibit further fracturing. This is because the stress doesn't align with the discontinuity's plane of weakness and instead can cause a compression effect. This compression can effectively clamp the discontinuity, making it more difficult for new fractures to form. These varying behaviors of discontinuities under stress highlight their crucial role in the overall fracturing process. They can either be the catalysts for new fractures or the guardians preventing further breakage. To sum it up, discontinuities are not just static features in the Earth's crust. They are dynamic entities that interact with incoming stresses in complex ways. Their orientation, the nature of the incoming stress, and the rock's mechanical properties all play a role in determining whether these discontinuities will promote or inhibit further fracturing. Pre-existing discontinuities, therefore, can significantly influence the fracturing process. Their role is not just passive, they actively shape the course of fracturing, making our understanding of them vital for predicting and interpreting geological phenomena. Under what circumstances can these previously fractured or faulted areas become active again? Picture this: an old dormant fracture lying deep within the Earth's crust. It's been quiet for millennia, but suddenly it reawakens. Why does this happen? The answer lies in the conditions for reactivation of pre-existing discontinuities. The first key factor is a change in stress conditions. Stress in the geological sense is the force applied to a certain area. Now imagine the Earth's crust as a giant jigsaw puzzle. Each piece or rock is under a certain amount of stress from the surrounding pieces. When the stress on a rock changes, it can cause a pre-existing fracture to reactivate. This change could be due to tectonic forces, such as the movement of the Earth's plates, or human activities like mining or reservoir-induced seismicity. Next, let's consider fluid pressure. Fluids, such as water or oil, exist in the pores and fractures of rocks. When the pressure of these fluids increases, it reduces the effective stress on the rock, making it easier for a fracture to slip or a fault to move. This is why activities like hydraulic fracturing or fracking, which intentionally increase fluid pressure to break rocks, can potentially reactivate old fractures. Lastly, let's not forget about temperature. Changes in temperature can cause rocks to expand or contract, altering their stress state and potentially leading to the reactivation of fractures. For example, in geothermal energy production, the injection of cold water into hot rocks can cause rapid temperature changes and potentially trigger seismic activity. So there you have it. Changes in stress conditions, fluid pressure, and temperature are all key factors that can awaken old fractures from their slumber. Thus, even old fractures can come back to life under the right conditions. The study of these conditions and their effects is not just fascinating, but also crucial for understanding and mitigating the risks associated with seismic activity. So what have we learned today about fracturing and reactivation of pre-existing discontinuities? We've delved into the basic tenets of fracturing, understanding its geometry and mechanics. We've discovered how the physics of stress and strain play a pivotal role in the process. We've also explored the concept of pre-existing discontinuities and how they can be reactivated under certain conditions. These discontinuities, or faults, are critical in understanding why and where earthquakes occur. This knowledge is not just academic, it has practical implications in several fields. For instance, understanding fracturing can aid in resource extraction, helping us to tap into oil and gas reserves more effectively and safely. In geotechnical engineering, it can guide us in building safer structures, particularly in earthquake-prone areas. By understanding the geometry and mechanics of fracturing and the conditions for reactivation, we can learn to predict and possibly mitigate some of the Earth's most powerful natural phenomena. Thanks for watching us share our videos, subscribe our YouTube channel, and press the bell icon and stay curious for new uploads.